Okay, I want to tell you about the dynamics of simple harmonic motion. Dynamics just means the way Newton's second law fits into simple harmonic motion. So let's apply Newton's second law. Let's figure out why it makes this motion in the first place. Okay, so here's our system. We'll look at other systems besides this one, but this is just the easiest one. No friction, just a spring that's going to oscillate this thing back and forth. So at any given time, if we want to know what the acceleration of this thing is going to be, like wherever it is, if it's a right here, then the spring would be stretched a distance x. Let's call this distance a distance x. It's not as big as a, it's just a distance x. Okay, if I were going to draw the forces on this here, there is mg down. There's the normal force up. And then there's the force of the spring, and it's this way. Force of the spring, that's F sub S. And so there is no friction. Now mg and the normal force cancel each other out. And so we're just left with the net force will be the force of the spring. So A equals F net over m. And so A equals, now the force of the spring, Hooke's law, now we have to get the positives and negatives right, because before we were pretty loose with whether or not Hooke's law was kx or negative kx. But now it's negative kx, and I'll explain why. That's the force, and then divide it by the mass. So A equals F net over m. Now why negative? Well, because this is a restoring force right here. That is a restoring force. And so look, it restores it, whenever you move something away from equilibrium, the restoring force brings it back to equilibrium. So if x is positive, if x is this way, you see how the math then tells you that the restoring force will bring it to the left then? But if we go into the negative territories where x is negative, if we make that negative, then we'll have a double negative. So now the force will be positive. So it's going to be pushing it to the right, trying to restore it. So what this means then, the way you can look at this is the negative is telling you that the force is always going to be pulling back toward the equilibrium, no matter which way. It doesn't mean the force will always be negative. When the x is negative, the force is positive. But we need that negative there. Okay, I'm going to rewrite this. It's going to be written like this. A equals negative k over m times x. Now, this is kind of interesting because A is the second derivative of x. And so this is saying that if you think about it, if we take the second derivative, I'm going to write the second derivative of x like this. It's the second derivative of x with respect to time. That it's equal to just a constant k over m times x. Okay, so what function can you think of that when you take its second derivative, you are pretty much back where you started from? So this is equal to that, except for some minor constant. Well, let's go take a look at our equations and see if we can't find that. We're back here. Here was x. It's a cosine omega t. And a is negative a omega squared cosine omega t. So these are almost identical. There's only an omega squared in there. So if we look, x, what I just told you is if x equals a cosine omega t, and if a, by taking two derivatives, we get negative a omega squared cosine omega t. Then this is A, and this is X. And what separates them is a negative sign, and then K over M. So that means that K over M, if you look, this K over M must be omega squared, because this is the same as that. So K over M must equal omega squared. In fact, I'm going to tell you that omega is equal to the square root of K over M. This is a big equation. It's a little equation. It's not a big equation, but it's used all the time in simple harmonic motion. So the angular frequency is equal to the square root of K over M if we're talking about a mass on a spring. Okay? So what that means is that since omega is equal to the square root of K over M, and the period is equal to, let me go back. Let me cancel that out. I meant to say omega is also equal to 2 pi over the period. Then let me set these two equal to one another. So the square root of K over M is equal to 2 pi over the period. Solving for the period, I'll bring the T over here and this underneath. Apparently the period of a mass on a spring is equal to 2 pi times the square root, and I'll take the reciprocal of that because I'm bringing it on the other side. I brought the T over here and this will go on the other side, M over K. That's another big equation. So if you want to know how long it's going to take for the mass in the spring to go back and forth one time, it's just 2 pi times the square root of M over K. So that's a big equation, and so is this one. There's one other important idea that came out of this video, but these are two big equations that you use all the time in solving simple harmonic motion. Okay. There's one more bit of important thing that comes out of this video, and that is that for simple harmonic motion, then this is what you need. You would like the restoring force. In fact, this is the definition. This is what defines simple harmonic motion. The recipe for simple harmonic motion for any simple harmonic motion is the following. You need the restoring force, the force that's restoring it to equilibrium, to be equal to negative K, a K being just a constant. It doesn't have to be the spring constant, just any constant, negative K times X. So let me write that in English. That's how you write it in math. But we would say the restoring force in order to get sinusoidal motion, in order to get simple harmonic motion, the restoring force needs to be directly proportional to the object's displacement from the equilibrium. But in the opposite direction. Out of time. Thank you. Bye.